Terrific. Okay, so let's go ahead and start off by just kicking off the Python session. We're going to move right past that, and our kernels will be ready to go when we get there. So last time we started talking about the expectation of a random variable. So the idea was to take a weighted average of the values that the random variable can take on, and the weights for that weighted average are just the probabilities of each outcome. So in short, we said the expectation of a random variable is defined to be the probability weighted average of its values. So we gave a definition that looked like this: the sum over all omegas in the probability space of x of omega times the probability mass function m evaluated at that omega. And I want you to decide which of these two statements you agree with. So kind of a mixed response here. Let's take a look at what folks said. So we had 5 people weighing in with, we could prove that this is equal to the probability weighted average, and 3 people saying, well, this is just what probability weighted average means. I guess you could argue either way, but I would go for this second answer here. To me, what does it mean to average a particular set of values with some weights? It means multiply those weights by those values and add up. And that's exactly what this says to do. So, if I wanted to make a proof having something to do with expectation, I would start with this as the definition of probability weighted average of its values, and then work towards some other value or some other expression that this is supposed to be equal to. And in fact, we will do that shortly for a particularly useful instance of this. But I just wanted to start out by demystifying the math notation a little bit. It's just saying all the x's, and then they get weighted, they get multiplied by the probability mass function. So this is literally just probability weighted average of its values. So let's take a look at this in a figure to try to really nail this down. So assuming I just gave the answer here that we've already talked through. So let's again consider the 2 coin flip experiment and the random variable, which says how many heads are in the result. So we're going to have a 2 down here and a 0 here and 1s on the corners. So if you adjust this slider, the description of the omega will fade out, and what will come in is the contribution of that little omega to the result. So we get a number of heads equal to 1 for these two. So we have a 1 there, and 0 and 2, as we said, and then all the probability masses are a quarter for this probability space. So we get a factor of a quarter for each of those. So this is expectation. We total up all of the contributions that you see here in this figure. Okay, so again, each outcome contributes the product of its probability mass, a quarter in this case, and the value of x on that outcome, either 0, 1, or 2. So based on this definition, it seems like we need to see omega in order to work out the expectation of the random variable. Like, we're looking at omega right here and doing some stuff with it, and we get some number. And it's a question, well, what if I just let you see the distribution of omega? I map all of these masses forward according to the function x to the number line, and I just tell you how much total mass ends up at each point after I've done that. I don't tell you anything about where the masses came from. It seems like you might be in trouble because we gave this definition in terms of omega. Does it actually work out? Yeah, so I'll ask you to commit to a thought about that. Maybe you know, or maybe you're having a guess. That's fine. Just choose one of these two. Either I think that 2 random variables can have the same distribution but different expectations, or I think that any 2 random variables with the same distribution must have the same expectation. So certainly one of those 2 statements is correct. Which one do you think it is? Split once again. Let's take a look at what people said. I'll try one more. A few people are still responding, I suppose. Okay, so again, we had more for the first answer than the second. Can you have the same distribution and different expectations? Well, let's just work it out. Instead of telling you the answer, let's look at a picture to resolve this question. So what I'm going to do here, this is the picture you've seen before, but now we have the contributions available as well with this slider. So we can either look at them as the original outcomes and map them over here where they go, or we can go ahead and look at the contributions that each one makes to the expectation and then map them over here. And the thing is, after you get them over here, what you can see is that if you have any number of masses at the same x value, then those masses are just going to add up, because the x of omega value at that particular point, it's all the same. It's whatever the value of that point is. So we're at 1 right here. So the first factor in the expectation calculation on both of these two masses is going to be 1. And that means we can just add up the quarter and the quarter here to get a half. So we have a half unit of mass here times the value sitting right there. That's the contribution coming from all those masses. Same here, there's only one mass, but still you can multiply the value 0 at this point by the amount of mass there, a quarter, and that gives you the contribution for that mass. Same here, 2 the location times a quarter the total amount of mass there. So that's it. If we know where the points are, we know where the probability masses are on the number line, and we know how much, well, yeah, that's it. We know at each point, like where the masses are and how much mass is at each point, then that's enough to work out all the individual contributions of each little x value, so like 0, 1, or 2 in this case, to the total expectation, and therefore we can work out the expectation because it's the sum of all those contributions. So yeah, just for posterity, explaining what the sliders do. I mean, you figure it out if you mess with them, but just for completeness. Okay, so in words, what we just said is that if you look at all of the masses at the same point x on the number line after you've pushed everything forward to the number line, it's going to contribute that value x times the total amount of mass there, right? And that's because x of omega is equal to little x for all of those omegas, just by the definition of how you push forward the masses. Okay, and then we can use the distributive property. We can state this as a theorem if we want. We can say the expectation of a random variable x can be computed as a sum of little x times the probability that the random variable x is equal to little x over all real numbers little x. So like this sum is written over all real numbers for convenience, because you can just say, well, it should be 0 if x is any real number other than 1, that the probability of x equaling little x is positive. So you could equivalently say for x in the support of capital X, or just all the ones where this contribution would be positive. But anyway, the point is we've now written the formula for the expectation in a way that makes it really clear it only depends on the distribution. If I just tell you the distribution, that's enough to go through and work out the total contributions of all the masses. So I kind of want to present this as well in the way that it's presented in data gymnasia. It's a little more intimidating. There's sigmas everywhere. There's some notation that you might have to kind of fight through a little bit. And the reason I want to do this is it's often the case that you're going to see some math notation that looks intimidating, but it actually maps in a pretty straightforward way onto a very comprehensible picture. Like hopefully in this picture, it's really quite clear that you're going to have all of the masses stacking up at a particular point, contributing the same x. So when you look at the x of omega factor for that mass, they're all going to be the same, so we can use the distributive property, right? So that this picture, you might need to look at it a bit longer if it hasn't come together for you yet, but it's not indecipherable here. We're not using anything really more complicated than just mass accounting. We're just totaling some stuff up, plus applying the distributive property. And the way we're going to present this here with a bunch of sigmas, it's really the same thing, but it just looks a little more intimidating. So this way, when you see formulas like this, you'll be prepared to sort of map them back to something more comprehensible. So effectively, what we're doing is we're taking this formula x of omega times n of omega, and we're grouping it based on where the masses end up. So if you have several masses that end up in the same place on the number line, in other words, x of omega is the same for all of them, then we're going to look at all those together. We're going to collectively group them together. So we split the summation over all the little omegas into two summations, one where we're summing over all the real numbers x, and the other where we're summing over all of the omegas where big X maps to that one. So it seems like we're summing over kind of way too many little x's here, but we really only end up getting contributions from the ones where capital X actually does map some mass to. So this is really the same formula. I'm just grouping some terms together. And this inner summation here, this notation at the bottom, I should make this zoom bigger. This notation at the bottom, omega and big omega, such that x of omega equals little x. What you're saying is I'm only considering these terms for this sum. So if you have a little omega where capital X of it is not equal to little x, then this it contributes nothing to this sum. So this is only considering certain little omegas. It's just a grouping operation. And then the thing is, if you know that x of omega is equal to little x, you can just replace this with little x, because in this inner summation, we know that that's the case. So we can pull it out and get something that looks like this. So it's really the same thing, except we just replaced big X with little x, and then because it was the same for all of them, we pulled it out. So that corresponds exactly to this distribution up here, this reverse distribution operation where we pulled out the 1 and said, let's add up the masses. And now, if you're totaling up all the probability masses associated with the outcomes that x maps to little x, that's just the same as saying the probability that x is equal to little x. So we can rewrite this like that in a way that gets the probability mass function out of it. And that's nicer. That's our final formula for the expectation of a random variable x in terms of the distribution of x. So again, just one more time, this all might seem kind of complicated, these formulas, but really everything there is mapping in a direct way to that picture. So this gives you kind of a good solid example of a dictionary between a proof that involves some sigma notation and kind of moving some symbols around, and a proof that involves looking at a picture and kind of arranging things in columns in a way that coordinates with your intuition well. And so that'll give you kind of hopefully a blueprint for doing that in the future. If you see you're reading a paper trying to understand some new technique and they bust out some math, you can kind of pull it back and interpret it in a meaningful way. Okay, I want to think about a kind of a modest modification of this setup so far. I want to give you a minute to think about it. And this kind of, the goal here is to help you unpack what we just did and own it a little bit. So suppose that we have a random variable and a function from R to R. So we can define a new random variable, which is f of x. So for each little omega, I figure out what x of omega is, and then I apply f to that number to get a new number. That's my new random variable. We call it f of capital X. How do I need to modify this formula to account for this extra application of this function f? So what happens if you imagine in this picture up here, after you apply capital X, you apply some other function f. How does that change the picture here, and how does it change the resulting formula? And I talked over a lot of that time, so I'll give you another 30, 40 seconds after the timer runs out. Because folks are coming in consistently, there are new answers rolling in that folks are putting together, and it's really, I think, super helpful to think this through carefully, because it gives you some agency in manipulating this figure and thinking about what's really going on here. So yeah, instead of sharing any of these answers right away or giving you the answer, I'm going to give you a picture to go with this so that you can kind of enhance the way you're thinking about this setup, and then you can think about what needs to be modified. So again, we're going to map everything to the number line for, again, this same random variable that we always look at. And then we're going to apply the squaring function. So the squaring function on 0, 1, and 2, it preserves 0 and 1. So they actually aren't going to move. But then the output, instead of 2, will be 4 after we apply f. So that means that this probability mass, instead of ending up at 2, it's going to end up at 4. So we move this slider and it's going to move over here. And since we're totaling up the value at each point, so the actual x value there on the number line times the probability mass there, this contribution increases. So all these other contributions are the same, whereas this one goes from 2 to 4. So really what's happening here is that the contributions for each of these little x's, instead of it just being wherever capital X mapped them to, it's going to be that, and then with f applied one more time. So if you look back at this formula, you have little x times probability, capital X equals little x. What changes here? So all these probabilities are exactly the same. Notice you have quarter masses here everywhere. Each mass, the amount of mass that that particular point represents, stays exactly the same. So we don't need to change this part at all. But here, instead of getting a contribution from the point x on the number line, we're going to get a contribution from f of x. So here it is originally, here it is afterwards. All of these 0, 1, and 4 values, these are the output values after you apply f. So the function f just moves all the masses from each location where x had sent them to a new location, f of x. So this is the only adjustment we need to make. So yeah, so I want to share some of these these answers now because we had some good ones. Okay, here's an interesting one. Let's see if we can find one from. So Nick, you had a correct answer and you had a check mark. So if you don't mind being put on the spot a little bit, what do you think about this answer, this second one here, which is only slightly different from yours? Yeah, what's going on is, of course, at some level, this formula has to be right because we're really just kind of sticking f of x in for capital X. We're just kind of plugging this into the original formula, not really trying to find a sort of minimal modification that gets the job done. And that's fine. And I think someone actually explained this point quite nicely. Yes, this is perfect. This is exactly what I'm looking for. Yes. Okay. So Nanga, do you want to talk about this because you're sort of elaborating on what gives rise to this formula here? Right. That's right. So the reason I think it's helpful to elaborate on that a little bit. I mean, it's absolutely correct. If you think of f of x as just another random variable, you can write down the same formula. The formula for expectation applies for any random variable. So in particular, it will apply for this one. The difference is that here we're writing this formula in terms of the distribution of the original random variable, with the idea being that let's say we know about the distribution of the original random variable and we don't want to work out the distribution of f of that random variable because it could be a little more complicated in some way. Like with the squaring function, if you have some probability mass at some negative numbers, they'll get mapped to some of the same locations potentially as some positive mass that was sitting at a positive number, since the squaring function maps, let's say -3 and 3 both to 9, for instance. And it can just be a little trickier to think about the distribution of f of a random variable. And this formula tells you don't have to. If you know the distribution of the original random variable, you can work from that and just include f only here in this one spot where you're changing what gets multiplied. So this is a super handy formula, even though, as you say, it's more straightforward in some sense to just work directly with that new random variable in principle. As it turns out in practice, it's often easier to do it this way. But yeah, that was a good explanation. People had a lot of good thoughts on that. Right. So yeah, so this is a great question that I think often goes unanswered. I'm glad you asked this question, Katie. What's the difference between f of capital X and f of little x? So, you'll see a lot of little x's and big x's and big Y's and little y's all the time when we do probability. And it's super important to nail down what this notation means when we're writing all of this out. So whenever we write a little x, we're always bearing in mind some actual concrete specific number on the number line. So this is not a random quantity. This is some specific number. For example, we sum over all numbers on the number line. We're saying, consider some little x on the number line, work out what the contribution is, what this term is when you multiply these things out, and then keep track of it. If it's 0, of course, throw it away because you're adding, so it doesn't matter. But if it's positive, keep track of it. And once you've totaled up over all the real numbers with a positive contribution, add them all up. That's the result. That's what you're going to call the expectation of x. So whenever you see big X, it's talking about the random variables. When we say probability big X equals little x, so this is an event, big X equals little x. So if I give you a little omega, you can tell me what big X of omega is, and then you can say whether that's equal to little x, which bear in mind is some specific real number that's being fixed for purposes of working out what this term is. And then that's an event, you can work out its probability. You can say just how much probability mass is associated with that event. And then you get a number. F of little x is also a number, because remember, f is a specific function, x is a specific number, and then that gives you some contribution. And then you work that out for all the little x's and total them up. That's what you get over here. So bottom line is that, as long as we're being notationally consistent, capital X is going to be a random variable. So, basically always, if we're being consistent with our notation, while x is a specific real number. So like, for example, in this formula, right? When you have a particular x in R, you work out what f of x is, f of little x, and that's some specific number. And you can ask what's the probability that f of big X happens to be equal to that specific number. Okay, so that's great. Yeah, I'm really happy to field these questions. I think, it's easy for me to forget what the, kind of really important things to clarify are as we go. And I think it's worth taking the time. We have the summer, we can kind of adjust how much material we cover. I think it's really important that people feel like everything is totally clear. Okay, so we talked about one other thing last time that I'd like to get into more now, which is Monte Carlo simulation. So we talked about how we can approximate the mean of a random variable by simulating it, even if we can't exactly work out the distribution. And the idea there was that if we sample the random variable many times and average it, so the ideas are going to be independent. When you do this in a computer, you call the random number generator function multiple times. It's going to give you fresh, nominally independent samples from that distribution. And we can use that to our advantage by getting many independent samples from the distribution of whatever random variable we're interested in. And the idea is that, well, if we average those, it should give us a good approximation of the mean of the random variable. We haven't at all said why that's the case. We'll be building towards that. That's a theorem, but I want to introduce this idea early on because it's a really handy way to kind of get a hold of the idea of expectation. So let's do this in an instance where it really is quite difficult to work out in some other way. So we're going to begin by picking a number between 0 over 1,000 and 1,000 over 1,000. So every integer between 0 over 1,000 over 1,000, that's our set. We pick a number uniformly at random from that set. So if that number is less than 1, then what we're going to do is pick another number independently from the first draw from the same distribution and add it. And now maybe it's bigger than 1. It has a better chance of being bigger than 1 than the first one did, but maybe not. And if it's not, then we just do it again and again and again and again until eventually the first time we see our running total exceed 1, we stop. And we're like, okay, however many draws we took, that's the value of our random variable on this particular run of the experiment. So capital X is a random variable. It could be 1 if you happen to pick 1,000 over 1,000. Then it only takes 1 draw. And it could be potentially very large if you happen to pick a whole bunch of zeros. Just, it's very unlikely, but if you picked a ton of zeros, it could take really a lot of draws to get over 1. So this is a random variable whose support is the positive integers. And it's really tricky to work out exactly what that distribution is, but it's much easier for us to simulate it. We can totally do this thing where we draw a number and we're like, hey, is this bigger than 1? If not, let's keep going, keep adding to the total and just see how it works out. That's very doable if we're, programming, but working out that exact distribution is much harder. So this is kind of a really mostly a programming exercise at this point, but I want folks to see if they can do this. So pull up your Python cell here. It should be live because you started it out at the beginning of class. So it should be good to go. And you can practice writing a function. So maybe start with NumPy import. And you're given in the problem statement, you're given this piece of code, randint 0, 1001 divided by 1000. This is a way that you can sample from this distribution that's given here. And so you have to supply the rest of it in order to play this game. And I didn't put a timer there. I'm just going to feel out how it goes. I think it's going to take a little bit of time. So here I'll share Jason's answer. Is very similar to mine. Lots of folks are working on this and making really good progress. I don't have a lot of answers like submitted yet, but most people are basically done. They have a sort of almost working example and they're running into, maybe like a little typo or something, a small bug here or there. But yeah, so this is what Jason wrote. This is what I wrote. It's very similar. And the idea is it's really nice to encapsulate one run of the game into a function so you can call that function repeatedly. And so what we're going to do is start with a running sum equal to 0 and initial counter equal to 0. And we're just repeatedly going to add a new draw and increment the counter. And once we're bigger than 1, we're going to break out of this loop and return the counter. Incidentally, I learned a trick with while loops that I'm just going to share. It's sort of unrelated to this problem in some sense, but it's my general advice for while loops. I got this from Stefan Karpinski, who's one of the co-creators of Julia. And I think it's excellent advice in general when you're writing while loops. So every time you write a while loop, you're going to have this problem when you write the condition down, which is what should the condition be? Sometimes it's obvious, and then you can just write it. That's fine. Most of the time, it won't be obvious exactly what to write down, or you'll end up in a situation where you know what you want to write here, but it won't be executable on the first run of the loop. So you have to repeat some code from the while loop above as well to kind of initialize things. And it's just annoying. So what you can do to solve this problem is do a while true loop. So in Sketch, this is called a forever loop, which I love. So the point is, it's just going to run this over and over forever. And then at whatever natural point in the execution of the body, you want to check some condition and decide whether to break, you just put that in. So I can run this while true. And then at the end, I can say if S is greater than 1, then break, right? That would be a fine way to do it. And then if it happens that you're going to want to put that condition in at the very beginning, then you can just check that here. But yeah, so in some sense, I think really a forever loop with a break condition inside is kind of a more natural thing than a while loop, because having to put the condition at the very beginning before the body executes is in a lot of cases kind of unnatural, and it sort of forces you to restructure your code a little bit in a way that's really unnecessary. And some people will say while true loops are the worst because you can forget to put in the break condition and end up with an infinite loop. But the truth is, you can end up just writing this condition in such a way that it never gets satisfied, like you forget to increment a counter or add to the value that you're checking something for here, and end up in an indefinite loop anyway. So it doesn't really change things. In both cases, you need to write correct code to avoid getting stuck in an infinite loop. So yeah, so just give yourself permission to write while true every time you write a while loop. Put a break condition wherever it comes natural. And then if it happens to be the first thing or can be the first thing conveniently, then you can just replace the true with that condition. Anyway, that's a bit of an aside here. So here we have a bunch of runs. You can see loads of them are 2s. None of them are 1s, but lots are 2s, quite a few 3s. 4s and 5s start to get fairly rare, but there's some of them. I don't see any 6s. Whatever. This gives you kind of a sense for the distribution of this random variable. And then if we want to work out the average, we can just do that, numpy.mean. And we get for, I just did 100 runs here. We get 2.78, 2.7, 2.64. It's kind of all over the place. If we really want a good estimate here, we need to do a lot more runs. And then we'll get much more meaning when we interpret the result. So yeah, here we have 2.717. That's quite accurate. We can run it again. You get 2.715. So it's starting to get pretty close to some value around 2.7 or 2.71 or something. Okay, so here's the solution that I have. Yeah, just same thing I typed in my pop-up code cell. I'll just check if anybody has any questions. I think we're good. Incidentally, this is really an aside, but I'm just curious if anyone sees that number and thinks, you know what, I bet that's actually fill in the blank. So so 1,000 is a little artificial here, but what if we replace it with n and then work out the answer to this question and then let n go to infinity? What do you think we're maybe going to get if you cross your fingers a little bit and trust in the beauty of math? Yeah, so if you don't remember, if you ask NumPy what the value of e is, exponential of 1, it's 2.718, and that's the right answer here. So I think it's kind of cool how you have this problem that, the 1,000 is a little artificial, but otherwise it's a very natural problem. You're just drawing some random variables from an interval, and you want to know, like, how long do I have to wait to see them add up to more than the length of that interval? And it turns out Euler's constant E shows up when you do that, which is pretty fun, I think. I don't know how you would have expected E to show up in that context. Then again, E shows up in a lot of contexts where it seems kind of surprising. So in that sense, I guess maybe you're already pricing that in, but Anyway, we're not going to show why this works out to be E just yet, but we'll have the tools to do that later on. Okay, so let's move on from expectation, or rather talk about a specific expectation, which is in some sense more sort of more prevalent, more prominent in statistics because it involves two random variables instead of just one. So the mean is a summary statistic for the distribution of a single random variable X. And covariance, likewise, is useful for summarizing how two random variables X and Y are jointly distributed. So here's the definition. The covariance of two random variables X and Y is defined to be the expected product of their deviations from their respective means. So the idea is we have to work out the expectation of X itself and then say, okay, X minus that. So sometimes that's going to be positive, sometimes negative. Unless all of X's probability mass is at a single point, it will sometimes exceed its mean and sometimes will be less than its mean. And you're just saying like, okay, how much more or less than its mean is it? And same thing for Y. So for each instance, little omega, each draw from the probability space, we can say what X of omega is, what Y of omega is. And these are just constants. So we can say, okay, was X above or below its mean? Was Y above or below its mean? And by how much, that tells us what these two factors are, and we can multiply them. That gives us a random variable. So for each little omega, we can say what that all of this stuff in the brackets is. And now we have a random variable. So it's a quantity that depends on little omega. And we can say, okay, what's the expectation of that? And we define this to be the covariance of X and Y. Instead of giving you a specific numerical example to work out, I want to give you a picture, and we can kind of talk through how to think about each of these examples. So I want to ask you to do this one because I want to take a little more time on it and kind of walk through it a little bit. So I want to look at each of these joint distributions and talk about whether they look like positive covariance, negative covariance, or zero covariance, assuming that there's one of each here in this picture. So let's take this middle one first. Maybe if you give me a second, I will. I do have to open it, but I kind of want to give myself a whiteboard. Whoa. Now I'm zoomed way far in once I've got the whiteboard. Okay, so let me just reproduce this figure. So there's like kind of a big mass up here and a big-ish mass right here and like sort of a small one there and then like a tiny one with it over here. So the first thing we have to do is figure out where is the mean of X. So we need to look at all of these masses and work out, okay, like where is it? Let me scroll down for you. We have to look at all of these masses and sort of work out like what's the center of mass if we take everything and project it down to the x-axis and then work out kind of the center of mass of all this. Where does it shake out? I'm going to guess, I don't really know. Of course, it depends on exactly what the masses are. But the point here is to kind of just eyeball everything. I'm going to guess that it's like right here. So this looks like maybe the mean of X, or maybe it should be over a little bit. Something like that. And then likewise, the mean of the Y's should be, I don't know, maybe something like that. So then what you're going to have is a contribution from this term, which is positive because the deviation right here, deviation in the X direction is positive from the mean, and in the Y direction is also positive from the mean. And it's like a pretty decent amount of mass, and it's pretty far away from the mean. So we get a lot of contribution here. And we also get a fair amount of positive contribution here because we have two negatives multiplying, negative deviation in this direction, negative deviation going down. So both of these are pretty positive and substantial. This is negative but tiny because the probability mass there is tiny. And remember, expectation is weighted by probability mass. And this one is also pretty small, not because of the probability mass, there's a decent amount of mass there, but because it's so close to the origin, the deviations are small. And remember, we're multiplying distances to the mean. So this is small. This is pretty big. This is pretty big. And this is also small. So all of this cashes out to be positive. So this is a positive covariance situation. So that's what's going on with this one here, is this positive correlation, or sorry, I haven't talked about correlation yet. This is positive covariance. This one, well, you tell me, maybe I'll ask that as a sort of insert an extra question here. So the very first figure is, are we going to say, is it positive or negative or 0? All right, so let's see. I'm going to say it's negative. And that's what most other people said too. Yeah, that's really good. I'll share the class response summary here. Most people said negative. And let's just look at that just to like really drive the point home. So I've tried to draw here sort of a eyeball estimate of the average of the vertical coordinates, so the mean of the random variable y. So we'll label that maybe expectation of y. Here's the expectation of x. If we call x and y the random variables that project each point in the probability space onto the x and y axis respectively. These are supposed to represent the means. And then what we're going to have from this point is a big negative contribution, because we have a big deviation in this direction and a big deviation from this in this direction and a decent amount of probability mass. Same idea here. And here we're going to have, both of these are going to be a small positive. Both of these are going to be a small positive contribution because they're so close to this vertical line here. And well, maybe the vertical line is on the wrong side. Maybe it should be over to the left a little bit, depending on exactly what the masses are. But the contribution would still be small as it's really close to this vertical line. And in fact, if this orange line should be moved over to the left, these would actually have negative contributions. So for covariance, deviation times deviation is positive up here because they're both positive. It's also positive down here because both are negative, and it's negative in these other two quadrants relative to the mean of the distribution. So this cashes out to a negative distribution. That's why this first one is showing negative covariance. I'll close. I have about a minute left. And I'll just say, so if one of these is positive and one is negative, and you're told there's one of each, this one has to be 0. And it sort of makes sense that that would be possible because the mean is going to be right in the middle of this rhombus. And like right there, exactly at the midpoint, the sort of common midpoint of these two line segments connecting the sort of diagonals of this quadrilateral. And these give negative contributions and these give positive contributions. And as long as the masses are tuned just right, those contributions could be equal. And given that the other two are definitely not 0, this one has to be the one that's 0. So I want to close with one question, which is, are capital X and capital Y independent if they're jointly distributed according to this third plot? So are X and Y independent in the third plot? Yes or no? Okay, great. So folks did a nice job on this one. Most people were able to answer this correctly. The easiest way to see this, I mean, there are lots of ways, but one simple way is to construct the product measure. So just project these points down onto the x-axis. You would have 4 places where capital X has support because there are 4 separate vertical lines that pass through some mass in the joint distribution. Same with Y. If you project this down to the y-axis, you'll have 4 masses. If you compute the product measure for 4 masses along the x-axis by 4 masses along the y-axis, you will get 16 positive masses in the plane for that joint distribution if they were independent. But that's not the case here. So in fact, if I tell you X, you know what Y is. If I tell you X is this value, Y has to be this one because it's the only Y that corresponds to that X. So this is, in some sense, way not independent. Either random variable tells you exactly what the other one is. Said equivalently, this measure looks nothing like the product measure of the 2 marginal distributions. So everyone who answered this question, no, answered it correctly. So this shows you that you can have, so no is the correct answer, since the measure you see there is not the product measure of the marginals. And that tells us that 0 covariance does not imply independent. I'll see you next time, next Tuesday.